Welcome to breadboarding. This is video 19 in the Nanocomp 6809 breadboard computer series. In this video I'm going to be adding a sound generator and a digital joystick to the project. In the last video I covered the background to the Nanocomp. It was based on an original project based in the 1981 Wireless World magazine, and over the series of videos we've built out the original Nanocomp and expanded it to include the features below. And then in the video controller series we built out a VGA compatible video card which included support for running Tetris, Lunar Lander and showing the Doom title screen graphic. In the previous video we added a PS2 keyboard, and now we're going to be adding sound card support and a digital joystick. So sound generation in early home micros and also in the first IBM PCs basically just used an input-output port bit for sound output, known as bit banging. This basically required quite a lot of processor time and programming effort to actually manage this. And around the late 70s, about 1979, then some programmable sound generator chips became available, and the one in particular we'll be looking at is the General Instruments AY3-8910, quite often just known as 8910. And this was used in arcade games such as Frogger, and also some of the sort of second generation home micros. So what this chip does is provide a 3-channel output with a noise generator and the ability to mix and determine the envelope for the signal as well. So this allows more sophisticated sound generation that will be capable of just doing the bit banging approach. Now, depending on the model of the chip used, there are a number of I/O ports included with the sound generator. So the one we're using, the 8910, has two 8-bit ports. The 8912 had one 8-bit port, and the 8913, which doesn't have any ports. And also note, when we're looking through the datasheets, the General Instruments datasheets are using octal base 8 rather than more typical hexadecimal base 16. So for example, if you see a table and it has 17 in it, then that probably means it's 0F hex or 15 decimal. These chips are available on eBay for a couple of pounds, a couple of dollars. I think I picked these up for £2 or £3. And I'm going to be using standard 3.5mm Phono socket to plug into some external speakers. So let's have a look at the data sheets and documentation on how we need to use this. So the basic data sheet is only about 8 pages, and you can see it's quite small. What I will do is just zoom into the pin layout. Basically the version we're using is a 40-pin chip. And you can see here that the sound output is on channel A, B and C. There is a shared data address port, so this multiplexes both the data and the address lines. These are all the I/O ports. So we've got port B 0 to 7, port A 0 to 7. Need to clock. These are some of the address line chip select signals, and it has a slightly unusual decoding from the CPU in that it uses BC1, BC2, BDIR, which I think was compatible with a General Instrument CP1600 chip this was designed to use. So it's a 40-pin chip. There are a couple of things which are not connected in the test, things we shouldn't be using, but mainly we're going to be needing to access the data lines, the bus control information and the outputs from there. So there's a more detailed document I'll come to in a minute, but there's a few key things in this sheet we just need to be aware of. These bus control signals, there are potentially 8 values in the bus control signals, but it does actually then later go on to state here, if we zoom in on that again, it does say that if BC2 is held high at 1, then in fact you can just use the bus direction and BC1 signals to actually control things. So whether or not it's inactive, read, write, or latch the address from the data into the address. That's probably what we'll need to use. So the diagrams in the other document are a little bit bigger. You can see that there's quite a bit of information about all the different registers. So there's much more detailed information about this in the other manual. So we'll handle that. This is showing the different envelope styles it's able to do, the different amplitude levels, and we've got a logarithmic D to A output. So I think she's got 16 levels, and you can see the sort of the variation in levels is logarithmic there. And then finally on the last page, there's a couple of things. It needs a clock. So the clock can be between 1 and 2.5 megahertz on this particular page. But the other thing I did notice here is the write data pulse width minimum here is down at 1800 nanoseconds. Now 1800 nanoseconds is quite a long time because the existing Nanocomp write cycle is probably about 500 nanoseconds. And when we speed it up to 8 megahertz, it will only be 250 nanoseconds. So this is something we need to be aware of, and that might determine what approach we use for interfacing this. So let's have a look at the manual, which is a much heftier document. So the various sources of this I found. This is the best one I found, and I will put a link to it. So it's about 60 odd pages long, so I'm not going to go through all aspects of it, but there are a couple of key things we need to pull out of here. So the diagram on the left here just shows with the General Instruments CP1600, which is why it's got these particular bus signals. And again, with the key thing really here is that the DA 0 to 7 actually used for the address and the data. And what it also says here is the 4 lower order address bits select one of the 16 registers, R0 to R17, so that's in hexadecimal. Sorry, that's not in hexadecimal, that's in octal. And the 6 high order address bits function as chip selects. So basically DA4 to DA7 are low enabled chip selects, A8 is a high chip select, and A9 is a low chip select. So effectively those higher lines just need to be held to low or high depending on the line. So this diagram's a little bit easier to see, and this matrix here will be used quite a bit when we come to doing the programming, but you can see the register numbers down here go from R0 down to R7, then R10 down to R117. So that's octal for 0 to 15 or 0 to F. And we'll worry more about all of the configuration of the noise generator, tone generators, amplitude control, envelope generator when we come to the programming side. So this document includes a lot more information on all the pins and everything. So I've gone through reading all of this, and I'll be feeding the output of that into the design. So the clock decision is quite important because the frequencies that we get out, depending on the configuration values, will depend on the frequency. I think the examples here have used a 2 megahertz clock. We could use a 2 megahertz clock, or we might just use a 1 megahertz clock. So this has then got the detailed information on each of the controls that we'll be looking at when we're doing the programming for this. Similar information that we saw in the datasheet, just a lot more detail. So then there's a sample clock circuit, which we're probably not going to need to use. There is an example audio output circuit. Now I'm going to be going directly to a 3.5mm Phono socket, so we probably won't need this. So I do have an LM386 if we do want to try the amplifier to go out to a speaker. So this comes into the microprocessor interfaces. So there are a number of different things, the PIC and the CP1600, which was a General Instruments. Then there is one for the Motorola 6800 series, so the 6809 being one of those. And it's relatively straightforward, if a little wasteful. It says use a peripheral interface adapter, so the PIA that we've been using for controlling the keyboard and the LED display, and use that and basically just use the port A to talk to the data address 0 to 7, and then use some of the port B lines to BC1, BC2, BC3. So although I was initially didn't want to go down this approach, with the timing issues that we identified in the data sheet, and also the fact that we're going to need another 4 or 5 bits for input from the joystick, then I thought, well, at least I could use port B 3 to 7 for the joystick as well. And there is obviously a little bit of assembly language code there. So we're going to use the peripheral interface adapter, and then that should make the programming a bit easier. This is an example of an Intel 8080 one, which was a little more complicated. Then as far as the music generation is concerned, there's a useful table here. This is based on the clock frequency based on the 3.57 megahertz sort of TV clock crystal, which tended to be used in a lot of early computers. And so this shows all the different notes we can get based on that frequency and what the 12-bit octal values are in the configuration registers for each note. So we'll have to generate that table for whatever clock frequency we choose, and then that should allow us to be able to convert music into the configuration needed for that. It also includes information on how to do chords, which is good. And then on the sound effects generation, there are some example configurations here. So this is like siren sound effect, gunshot, explosion. So those may very well be useful for the Lunar Lander game, certainly explosion, and some form of engine sound we'll need for the thrust, laser, whistling bomb, and race car sound effects. So hopefully with those examples, which we can use in testing, then we should be able to find something which will suit some of the games. And then finally in the specification section, we can then see here, if we zoom into it, so you can see here slightly inconsistent information. The clock frequency here is 1 to 2 megahertz, but the other one was 2.5 megahertz. But the right pulse data width, which was 1800 nanoseconds in the previous one, is only 500 here. So, you know, one or other of these data sheets is probably not accurate. But I figured if we use the peripheral interface adapter, then it won't really matter too much. So what I've got here is this is the General Instruments AY 8910. So hopefully this is a genuine part and works. The peripheral interface adapter, I've actually, because in one of the next videos I'm going to upgrade the clock in the Nanocomp to be twice the speed. This is actually a 68B21 chip. This means it's capable of running with the 8 megahertz clock. We also need a 3.5mm Phono socket, and you can see this is a PCB mounted one. Now the pins here, we've got the ground pin, we've got the tip and the ring and the sleeve pin. So the sleeve is the ground pin, the tip will be the left channel, and the ring will be the right channel. If we actually look at a cable, you can see, so that's the tip, that's the sleeve, and that's the ring on these. So we need to create a little adapter for that, and what I've done is used a bit of strip board. Just need to drill it out a little bit to make the holes a bit bigger. Then some 0.1 inch connectors. What I do with these is actually push the pins so that they actually go fully into the top of the plastic there, and then I actually put them in like this. So this is the connector that I've created. So you can see here that what I do is I solder the pins on this side and just push them all the way through here, and you can see we've soldered all those in. It's fairly straightforward. So we've got the 5 pins there. 2 of the pins are just used for the switches, so that if you wanted to hook this through to an internal speaker, then they would be connected through the pin there and the pin there, and then when you plug the socket in, it disconnects those. But we're really interested in the tip, the sleeve, and the ring, which is the left, the ground, and the right. So that's what we'll be connecting that into. So I've got the schematic here. I've updated this with both the joystick and the sound generator processor. So we've got the joystick configurations down here, which I'll talk about once we've done this one. So I've had to move things around a little bit. It's all getting a bit messy. Could really split this down into different diagrams, but I really wanted to just try and keep it all in one diagram if I could. Here's where the PS2 keyboard controller is. So what we've got here is our peripheral interface adapter. So this is just hooked into the data lines. So you can see here that we've hooked in the address lines A0, A1. Now what I've done here is this one's been wired incorrectly, so A0 goes to RS0 and A1 goes to RS1. The original Nanocomp design actually swapped these two address lines with the registers around, which has caused some confusion over time, but because the original ROM I had it that way, then I needed to do that. But it has caused me a bit of confusion from time to time, so I'm going to plug this in the correct way around. We've also got all the usual signals we need, so the E clock signal, the read-write signal, and these are all going off to the other parts of the board. And then the chip select here that we're using, I've actually reused the CRTC decode and I've now created a PSG entry for that. We go up here, so the Y4 signal is what we use for the keyboard, and now I'm going to use the Y5 signal, and so this is now, I'm calling it, it's actually Y3 because it's the Y3 signal from here. So this is the Y3 signal that's then broken down into these 7 values. So this is a Y3 PSG, I've called it. Probably my naming scheme is not the most obvious, but if we so that's where our chip select for this port is coming from, and then on the other side then we can just see it's fairly straightforward. We're just wiring port A over to the DAO, so that's going from PA 0 to 7 down to here, and then we're using port B for the BC1, BC2 and BDR. BC2 I think could just be pulled to 5 volts, but we'll connect it up, and that's what they've said. And then I've used these other lines here of them being used for the inputs from the joystick controller, so we'll cover that in a few minutes. And for the moment, what I thought for the clock signal, at the moment the E clock signal from the processor is 1 megahertz currently, so I think I'll just hook up the clock to that to be 1 megahertz. When we upgrade the CPU, it will then go up to 2 megahertz, so we might just need to make allowances for in the test programs to allow for the clock speed, but I think doubling the clock speed is not going to cause too much of trouble. And then when we go further down here, the outputs of the C, A and B, this is a circuit that I came across in one of the other designs that I've come across on the internet for output from this, and I think this is just sort of, rather than just hooking it straight up to the output audio jack, this probably is just a little bit better idea to adjust the levels and to do some sort of filtering. So we can see what the output looks like before this and after it, and we'll just be plugging in our Phono socket breadboard adapter there. Okay, so it's fairly straightforward. The main issue with this is really going to be how to wire into the rest of the board. Okay, so what I'm going to do now is to get the breadboard out, plug in the chips and wire it all up, and then once we've done that, we'll come back and we'll look at the joystick. Okay, so I've printed out the schematic, so I'm just going to plug the chips in now. I need to decide how many spaces to leave on each side, so I'm going to have the data signals coming in here from the main board, but then I want to then also piggyback the PS2 controller off there. So I think what I'm going to do is to give more space on the data bus side. It gives me a bit more space for plugging things in. I'm going to go all the way up to the top here. I don't normally go all the way up to the top, but I think by the time we put the other chips in and the analog to digital conversion circuit for the joystick, we might run out of space, so I'm going to move it up here. So let's plug that in. We've also got the chip label on there. Okay, it's in. And then for the sound processor, those are the data bus lines, and they need to be on the same side of the port here. So I'm going to put those in here and just make sure that we've got the voltage rails lining up with a thing there. So we're not going to be using that side much apart from the outputs there. So I think we can move this one down a little bit, move that over on that side. Okay, and then this is going to fit in along here somewhere when we know where we want it to be. So let's now going to hook this up and check things off here, and I will speed that up and we'll come back once we've got all of the wires plugged in here. Then we're just going to need to plug in the flying leads to come into the main computer here, and then put in some cables to go off to the PS2 adapter as well. Okay, so just wire up the power lines for the 2 chips, check those off the diagram. Now we're going to wire in the pins that need to be tied to +5 volts or to ground, so things like chip select signals. Check those off. Now we're going to wire in the output for port A and port B over to the sound generator chip. I did forget to record the video for the reset and the E signals, those blue wires coming through there. We've also missed out the reset signal on the schematic diagram, so we're just going to need to add that back in once we've finished the video. Okay, so we've done the digital side of the circuit, apart from hooking in the bus signals and things to the PS2 keyboard controller and the rest of the Nanocomp. So we're just going to do the analog signals now, so that's wiring up A, B and C over here. So I'm just going to plug in the connector first. This should just hang over the board so it makes it sort of nice and sturdy. Now we're not going to bother with stereo for the moment, so I'm just going to wire up the left and right, so that's the tip and the ring connectors. And then we need to connect the ground to the ground, so I'll do that on the other side over there. Okay, so now we need to connect the input to the 3.5mm Phono socket with this 2.2 nanofarad capacitor. So that is going over to this rail here, and then the 10 nanofarad then needs to tie this join here to ground as well. Okay. So in there, then we need the 470 ohm resistor in parallel across there. So 470 ohms is yellow, mauve, brown. It's tied to ground. Then we need to connect the A, B and C together, so I'm just going to wire B and C together there. Okay, and then I've got a wire I've already made to join C round to B. Then we need this 1K resistor going from A, B and C down to ground as well, and that's probably easier to wire that up on this side here. So that's ground going up to C. And then finally we need this 4.7K resistor, so that is yellow, mauve, red, and that's going from over here to our connections over here. And then finally we just need to do the decoupling capacitors, so I'll just put a decoupling capacitor near the ground signals for the two chips. So the ground is over here. Okay, so that's everything, and I'd already checked everything off. Unfortunately, the first time through I did this, the video stopped recording halfway through. So hopefully we've now got everything wired up except for wiring it into the main control signals and the main Nanocomp. So what I'm going to do now is to look at the joystick port, and then we'll wire up the joystick before going on and testing it. So let's have a look at the joystick. This is just a cheap analog joystick, Arduino compatible. Cost about £1.18 from Bitsbox, which is where I get some of my smaller components. It's just local, so I can just go and collect stuff. No need to wait for the post. And you can see that it's got a 5 pins ground plus 5 volts. There's an X and a Y and a switch. So it's very simple, but this is analog, so these are variable outputs, and what we want is to really just know whether we're left, right, up or down, or the button's been pressed. I was looking at various designs on on the net, and I came across some which were using the analog comparator. So this is an LM339, so it's a quad comparator, and all it does is compares two input voltages, and based on if one is bigger than the other, then it will cause the output to drive open collector output, so it can drive things to be low, or it can allow things to be pulled up to be high. What we're going to do is to just have a look at the joystick and to work out how to do this. So let's just get rid of the sound there. So here is a joystick. You can see that there's the ground, plus 5 volts, VRX, VRY, and switch. So at the moment, ground is black, plus 5 is white, grey is X, purple is Y, and blue is the switch. So all I've done is wired this up to a breadboard here, and I've just got my meter. At the moment, I've got this on continuity testing. So for example, if we plug in to ground and we plug into the switch, if we've plugged in one side to ground, the other side to the switch, and if we press the switch, so basically the switch grounds. When it's pushed, it will actually tie it to ground, and because the input to this only has ground plus 5, the X and Y outputs, and the switch, it's not like we can control that. So we need to make sure there's a pull-up resistor for the switch, and then when it's pressed, it will take that low. And then what I was going to do, the easiest thing to look at here is to just plug in some power, and if we plug the voltmeter, put it on volts now, and put it on purple, which I think by default is the vertical. Just switch on the power, so it's only set to 5 volts. And we can see here on the meter that in its neutral position it's about 2.5 volts, just under 2.5 volts. If we push it up to the top, it goes down to 0. If we put it down the bottom, it gets close to 5 volts. So it starts in the middle about 2.5 volts. Up is 0, down 5 volts. If we plug this into the grey lead, which is X, then we'll see again it's just under 2.5 volts. To the left is 0, to the right is almost 5 volts. So what we really want is that we only want this really to start showing left once it's a little bit away from the middle. We need to set a threshold really between the centre position, and we only want it to change after that centre threshold. So probably about 20% of the voltage or something would be good. Okay, so what I'm going to do now is just to look at the comparator, and we'll look at how we need to do that. So the circuit that I came up with, this is actually it in the diagram, in the schematic diagram. So over here, what I've got is our Zener diode circuit. This actually reduces the 5 volts down to about 2.3 volts in this particular case. And what that 2.3 volts is doing is going over to go and feed the VCC, or the 5 volt line, going into the joystick. I don't think there's any electronics in here, it's just resistors and things. So we're feeding the 2.3 volts into the joystick, and so the joystick outputs will be going from 0 to 2.3, 2.4, and it sort of is about 1.15, I think, volts is around the middle range. We're also then needing to produce a low reference and a high reference, so we need 2 voltages. So if we've got, say, 0 to 2.3 volts, and in the middle will be about 1.15 volts, then in fact we're going to want a voltage either side here, where if it goes below that or above that, then we're going to say, yeah, the switch is on. Okay, so what this little circuit here does is it's actually a 4.7k trimmer, 4.7k resistor, 4.7k there, and we can adjust the trimmer to make this bit wider or narrower. So really that trimmer just allows the voltages here to come closer to the midpoint or to come further away. This produces a low reference down here. So this is the low reference, and this is the high reference, and this is used to feed in the comparator signals depending on the conditions we need to actually give us an output for the right, for the left, for the up and the down. So it took a little bit of experimenting to get this working, and what I have got here is the circuit that I had got working. It's a little bit messy because it's just sort of in prototyping mode. What I'll just do is to connect the joystick to here. Okay, so I've hooked up the circuit and I've now got the power on. So we'll just show, so we've got the power going, which is just under 5 volts. If I take a feed off of the Zener diode output, so this is our voltage, so that's about 2.3 volts, which is what's going into the VCC line of the joystick. So I've got the voltmeter now on the grey lead, which is the XY one, and if so, you can see there the center point voltage is about 1.16. So we just make a note of that. So it's 1.16. That's X. And if we go to the right, it goes to about 2.3 volts. If we go to the left, it goes to 0 volts. So left is 0 volts, right is 2.3. And then if we put this on the purple, which is the Y component, so you can see that for Y is about 1.154. And if we go to the top, we get 0. So top 0 volts, and bottom 2.3, or down. Okay, so that's just showing that the range that we're getting there. So now if I then just check the voltages on the, so this is the low reference voltage. So this is about 0.8 of a volt. So if anything goes below 0.8 of a volt, then it will be considered to be low. And then if we look at the other line, this is the higher voltage. So this is a high reference voltage, it's about 1.48. So the reference is, so ref high 1.49 and low was 0.835. 0.835. Okay. So now when we plug the voltmeter onto the output 1, so this should be our left. So when we go right, nothing changes. When we go left, we get 5 volts. So that's good. Then we go to the second output. When we go left, we get nothing. When we go right, we get 5 volts. That's what we expect. Good. And then we'll do the Y one. So on the third one, this one, when we go top, doesn't change. So we go down. So the third one is down, is 5 volts. And then we go to the fourth output. If we go up, we get 5 volts, and down we get 0 volts. So four is up, 3 is down. Okay, so it took a little while to work out this circuit, and what I have got here is a little trimmer variable, trimmer potentiometer, and it's a sort of a 10-turn one, so we can actually vary the range. So if we were playing games and things and find that it's a bit too sensitive or not sensitive enough, then we can actually narrow the range over where the switch kicks in. And so if we now go back to the circuit diagram, so we can see that we had our 2.3 volts from this Zener diode circuit, that we had our high voltage, I think the reference high voltage was about 1.49. So this high reference was about 1.49 volts. The low reference was about 0.833. And the midpoint was about, when it was in the middle, it was about 1.16, 1.15, which is what I said here. So it's about 1.15, 1.16. So these combinations that we've got here, you'll see that there's various combinations of plus and minus going to either the reference or the low reference, and that these combinations were worked out to actually produce the right output for when the joystick goes right, left, up and down. So we just need to wire this into the board, and then we'll be ready to test it. Okay, so just plug in the comparator chip and the joystick outputs and wire in the power for the comparator and decoupling capacitor. Just need to move that over to make space for the pull-up resistors for the 4 outputs comparator. Check those off the diagram. Now we need to put in the resistor and the xenodiode to provide our 2.3 voltage reference. Now put in the potentiometer, which provides our sort of trimmer to be able to vary the zone in the middle where we switch from left, right, up and down. Then these are the resistors needed to provide the voltage reference for the low reference and the high reference to feed into the comparators. Tick those off. Now we're wiring together the input to the comparators, and we're going to now connect up the outputs from the joystick to those comparators. So that will be the X and Y and the up and down. Now we need to wire in the voltage reference sources, so the high and the low reference are now going round to the comparator inputs, and we'll check those off. So this is the last of the voltage references we're putting in there. Now we just need to put the pull-up resistor for the fire switch. Check all that off. Now we're going to wire in the outputs from here, so the fire switch goes into port B, and then the other 4 outputs are also then going into the port B of the PIA. Check that off. Okay, so you can see here I've hooked up the programmable sound card and the joystick, and you can see here the joystick's plugged in over here. All I've done is I've piggybacked it off the keyboard controller that we did in the last video, so it's just basically the data leads, there's reset, read write, the E signal, and then we've also got the CRTC address enable 5 output, which is going to our chip select low there. So that's plugged in there. I've also then got the address A0 and A1 lines coming in here, and these are wired the correct way for this particular chip, unlike the keyboard PIA. And everything's all plugged in. I've also got an old set of speakers plugged into here, so hopefully if I mess up, at least I won't blow up my main speakers. So this is all ready to run up, and in fact I have powered it up already just to do a few tests. I've got the logic analyzer attached to it, so what I'm going to do first of all is have a quick look at the programming of what we need to do, and we'll do a simple test program to start with, and then we'll do a slightly more extensive program to test it all out. So if we go back to the General Instrument AY38910 manual, so this was like the 60-page document, there's a block diagram, and in interfacing the electronics, then we've already handled the bus direction, BC2, BC1, the data and address multiplex lines, reset, etc. And we can see here that the registers which are used to configure this is all in octal, and I've got a slightly larger one of these in the slide deck. But basically we've got R0 through to R17, but that 17 is in fact 17 octal, which is in fact 15 decimal 0F in hexadecimal. This is basically the registers that we'll be using to configure it. What we generally have to do is to latch the address first of which register we want to talk to, and then we write the data. And if we look at the other side, then we can see these are these are facilities we've got. So we've got one noise generator for which we can configure the pitch of the noise. We have 3 independent tone generators for which we can determine the frequency of each of those independently. We've then got mixers which determine whether or not we bring in noise on each of the ABC channels and whether we bring the tone for the channels. Then we've got amplitude control, so we can determine the amplitude of each of the A, B and C individually, or we can choose to have the amplitude controlled by the envelope generator, and the envelope generator allows us to have a bit more flexibility in how the sound appears. And then this all goes out to the digital analog converter, which is where it's then going out onto the analog side of our board, where it's going off to our 3.5mm phono plug. So this is blown up a bit of that diagram. So remember again that the register values here are in octal, and you can see that some of the registers are 8-bit and others have varying number of bits. So the coarse tuning is how many units of 256. So we've only got 4 bits there. So we've got the A, B and C tone, we've got the period control for the noise generator, and then the enable here is whether or not the I/O ports are A and B are input or output, whether or not the noise is enabled on each of the A, B and C channels, and whether the tone's enabled on these channels. And then on the amplitude, we can control between 0 and 15 the amplitude of each of these channels. And then there's also a bit there that we set to say whether or not we want the amplitude to be controlled by the envelope. The envelope then has got 2 controls as far as the period of it, and then there's a shape which I won't go into detail now, but you can have different shapes for the envelope, so whether it's rising, falling, sustaining, alternating, various other things. And then finally we've got the port A, port B. We can only do them in input or output at the port level, not at any more finer grain. So I don't know whether we'll end up using those ports, but they're there should we need them. So the simplest effect they include in here is basically a sort of a 2-tone siren, a bit like a police siren on the cars over in Europe. And you can see here that register 0 is setting channel A tone, so this is setting it to about a 440 Hertz, which is about an A, and we're setting that with both R0 and R1, so that's the higher one. Then we're just enabling the tone only in channel A and turning off all the others. Then we need to set the maximum amplitude, so 1/7 in this is in fact 15 decimal. Then wait for a period of time, then change the tone to be a lower tone then, so 187 Hertz is lower pitch. And then after we've waited, then we'll turn it off. What I've done with the code here, I've taken one of the existing test programs I had from the keyboard, because we need to have this sort of CRTC initialization and palette initialization, just because we haven't added those to the monitor yet, but that will be coming. And then this is the siren in figure 27, which is the one we were looking at here. And in order to make this a bit easier, in the header file here, a lot of the configuration parameters and things are actually defined in the header file now. So you can see here I've got the programmable sound generator ports, so port A and port B and the control ports, those are defined in here. We've then got all of the chip register addresses, so these are 0 to 0F, 0 to 15, so these are the different registers that we've got. And then for each of the registers there are different sort of parameters that can be used, in particular the mixer, about whether or not we want to include ABC, noise, tone and various combinations. And obviously there are some combinations down here where you can enable or disable all inputs together. And then amplitude control, in particular whether or not we want to enable the envelope control. And then these are the different envelope types that we can have for affecting the amplitude. And then finally down here, these are the bus control signals, so the bus direction BC2, BC1 values. So we've got the ones for inactive to make it 3-state, latching the address, reading data and writing data. So those are all the things we're going to need to do for talking to the sound chip. And then I've also then extended the Nanocomp to include the Nanocomp file here, C file here. So we've now got initialization of the sound PIA. So this basically sets the ports up for port A to be output, port B to have the lower 3 bits output and the upper 3 bits are input. So that's used for the joystick. And then we set the control register to enable port A, port B then to be the data registers. And then we've got some helper routines. So one which says latch the address. So if we send the address here, it basically puts the address on port A, sets the control signal on port B to latch the address, and then sets it in active. Then to write, we do a similar thing with the data. All we do is we write the data out to port A. We then send the control signal to write the data, and then we make it inactive. And similarly for reading the data, we need to do a little bit more here, just because by default I'm leaving the ports in output mode by default. So if you want to read something, we actually need to set the port to be read and then set it back to output mode afterwards, so that we don't have to keep on doing this. The number of times we're going to read stuff from the chip is a lot less than we're writing. And then there's a simpler routine here that basically outputs the address and write the byte in one go, so that it makes things simple. So that should make programming the sound chip a little bit easier. And in fact, what we've now got here is, if we look at the code here, so though this is just saying which registers need to be set to which values. Now the only thing we need to be wary of here is that the frequency here is 1.7 megahertz, and we're only using a 1 megahertz clock, so we do need to adjust some of these frequencies. And so what we've got then is we are setting the initial starting frequency. I think this was, the A, 440 hertz. We're enabling we're setting the mixer to disable the noise, to disable B and C and only have A effectively. We're setting the A's amplitude to be maximum. And then this delay function is one of the Nanocomp delay functions. It's basically this simple siren, basically just alternates them between the two tones, and then at the end just sets amplitude to 0. So all I'm going to do is to compile that, and then we'll also run the logic analyzer on it as well, so we can see what's going on. So this is sound 1, so let's just compile that. I'll just send that down onto the Nanocomp. So if I put the Nanocomp into load, I'll just send this. Once that's been sent down, I'll then so that's loaded. I'll just get ready to run it. And all I'm going to do now is to go into the logic analyzer here, and this is triggered on the programmable sound generator address select signal. So when this is first accessed, it will start the capture, and it should be about 4 seconds worth of data. So we'll just run that there, and I'll now run the program. You should just hear in the background the sort of siren sound. Okay, so that seems to work. And if we have a look here, what we can see on the logic analyzer output, that we've got the programmable sound generator chip select here. And if we drill down into this, what we'll actually see is, so what I've got is the data lines going into the PIA, the read-write signal, and then whenever we're enabling the PIA, then this is how we can tell what's going on there, and then we can tell which register's been written on the PIA between the A0 and the A1 signal. And then when we're actually writing to the sound generator, then the bus direction BC1, BC2 lines will be toggled, and these are connected to port B. So we can tell when we're actually writing to the programmable sound generator. Now I know that some of the early stuff here is just initializing the peripheral interface adapter, set all the input and output lines. And then over here, then what we're actually starting to do then is to talk to the sound card. So to start with, we've got 0 there, which is probably disabling it. Then we've got various other signals going out, so 0, 7. And then you can see here that in fact, as a result of that we've actually got the bus signals are going high there, so that probably means we're latching the address that we want to talk to. And you can see here that we've got further updates occurring. So the fact that we're actually getting some sound out of here indicates that this is probably working. So these are basically setting the ports up for the one particular set of signals, and then for about a third of a second later, then we're doing the next frequency. So this will basically be toggling the two frequencies at the moment, so I'm pretty sure if we were to go into here, we probably would see what the different frequencies that are being output. Okay, so it seems to be working. I haven't tested the joystick yet, but what I've also then done is, once I did that basic test, I've got a more complicated test here, and what this has done is gone on, we've got the basic siren here that we started with, but then within the documentation there are further examples. In particular, we've got a gunshot effect, which obviously is going to be useful for certain games, and the explosion. In particular, the explosion I thought would be useful for the lander game. I also need to look at creating kind of a thrust sort of noise signal, so I'll have a look at doing that before we update the lander game with that. What I've done then is to add those two examples further on down here. So you can see we've got the gunshot, where we're just using noise. We're setting the amplitude just to be noise for, and then we're using the envelope period, and we're using a relatively short envelope period. And then for the explosion, we're actually using the lowest frequency noise period, I think, that it can support. And then we've got a longer period for the envelope control, so this explosion will last a bit longer. And then one of the things I was looking at is trying to find some sort of Tetris type tune. So the Tetris tune is actually Korumbienki. Apologies for anyone from Russia, but it's basically it's a well-known sort of folk song type thing. So it's not actually copyright. What I've done is taken some of the notes off the web where they've said what the notes are. The timing isn't quite right yet. It needs a bit more work and really need to use a MIDI file or something like that to get the timing right. But you can see here that we've put in the different notes and things here. And in order to do this, what I had to do was to, if we go to the document here, there is a chart that shows the different octaves and notes. Now the only thing is this chart is generated for 1.7 megahertz, so I needed to create my own one. So for each of the notes, the ideal frequency and the actual frequency is based on what the value in the registers are for this. So what I've done is a fairly simple spreadsheet, which was done for every combination, register combination from 4,000 down to 1. Basically, I've then gone through and actually updated where the individual notes and their octaves are. So we can see here that if we wanted the 440, for example, 440 hertz is A in the fourth octave, and that's a value in decimal of 142. And then here we've broken out the high byte and the low byte should we need it. So by plugging in these values into here and using the ideal frequency and this table to look it up, then what I've been able to do is to program in here the values. So we've got the A to G, and then there's a higher octave A there. So that basically just gives us our notes, and then here all I'm doing is a very crude delay between each of the notes, and there's a few areas where the pauses between things aren't quite right, but it sort of shows that the tune is recognisable if it's not a particularly close rendition of it. And then finally down here I've got a bit of a joystick test. So this reads the joystick value, and then based on what the joystick value is, it will highlight the left, right, top, bottom, and will also, if you click the button or the fire button, then it will just the bullet sound. So just going to compile that. So we'll just bring back this and do number 2. What I will do also is then share the video on the screen, because it will sort of show the joystick values and things on there. So we've compiled that. Let's just load it onto the Nanocomp. So Nanocomp's now in load mode, and we'll just send number 2. So that's loading, and whilst we're doing that, I will just share the, wait for that, it's complete. So let's just share the VGA capture. So hopefully you can see that. We can see that that's the default Nanocomp boot screen. Because the palette initialization has already been run once since power on, then it's already got the correct color palette. So all I'm going to do now is to run that second test program. So you'd expect to hear the siren, then a bullet sound, then an explosion, and then the sort of Tetris sounds, and then finally we'll be running into the joystick test, which will appear on the screen. So I'm just going to run that now. Okay, so that's a bit rough, but yeah, I think it's noted, it's recognisable, if not a perfect rendition. And then this is the test page that I've got for this. So all I've got here, I'm just using the joystick, and if I move it to the left, highlights left. If I move it to the right, highlights the right. Down, up, get up. If we do two together, we can, if we move the joystick around in a circle, you can see that. And then finally, if we press the fire button, and you can also see, because it's polling the joystick and updating the screen all the time, you can see that we've got the video update snow, and this is one of the things we'll be looking at addressing in a couple of videos time, is to try and avoid this this snow appearing on the screen. And this is caused by the CPU and the cathode ray tube controller chip trying to use the RAM at the same time. Okay, so it looks like it's working, and the programming really is the biggest area that needs work, and really ideally probably something that would read MIDI files would be good, but it's quite awkward doing the timing for this. And what I'm going to do now, if we just go back to our slide, so we've added sound support and the digital joystick. And what I will be doing in future videos is adding that support into the Lander game and the Tetris game, so at least we've got those sort of in a finished state. In the next video, what I'm going to be doing is upgrading the CPU to use the faster version of the chip. So the 68B09E is the 8 megahertz version of the 6809, but this E version does not have the clock generator circuits built into the chip, so we are going to need to add some clock circuits to be able to provide the right E and Q timing signals. This will also allow us to include the cycle stretching within that circuit. So if we need, for example, to stretch the CPU cycle a little so that the CRTC can keep access to the RAM whilst it's using it and then release it once it's finished with it. So that's what we're going to be doing next, is upgrading the CPU, and that's going to require upgrading some of the chips as well to the faster versions. That's the serial chip and the peripheral interface adapters both need to be upgraded. All the other chips should be okay. Hopefully you found it interesting. If you don't want to miss out on future videos, please hit subscribe, and if you found it interesting, please hit like. Thanks for watching.